Bismillahirrahmanirrahim. Assalamu alaikum students. This is your 13th lecture of physics for 10th class. This is your geometrical optics, that is your unit number 12, and this is the last lecture of your first term. The learning outcomes for this lecture are critical angle, total internal reflection, calculation for critical angle, applications of total internal reflection, refraction through a prism. Now today's first lecture is about critical angle. What actually is critical angle? I'm going to discuss the definition first and then I'm going to explain it. The angle of incidence that causes the refracted ray in the rare medium to bend through 90 degree is called the critical angle. As you can clearly see in the figure, I prefer that you are going to see the second figure, in which the light source is placed in the denser medium and the light rays are emerging from the denser medium into the rare medium. Now you should know what is a denser medium and what is the rare medium. Denser medium is the medium whose density is high and rare medium is the medium whose density is low. So in this case, we are going to place a light source in the denser medium. It can be water or it can be a glass. And the rare medium is your air. So the light source is placed inside the denser medium and the light rays are going to be emerged from that light source. There are 4 light rays which are going to be discussed here. So all the light rays are represented by the blue rays. As you can see that the first ray which is going to be emerged from the light source is moving straight away and enters inside the rare medium without bending. Why is that so? It happens because this light ray travels along the normal, so it does not make any angle with the normal, so that is why it will move straight away. Whereas the second ray, if we are going to see the second ray, when this ray emerged from the light source and hit the boundary, it will bend at a certain angle. And as you can see that the angle formed in the denser medium is smaller as compared to the angle formed in the rare medium. So all the angles, whether the angle of incident or the angle of refraction formed in the denser medium, always smaller, and all the angles formed in the rare medium, whether those angles are your incident angles or your refracted angles, are always greater. So in the denser medium, all the rays are bended towards the normal, where when these rays are emerge into the or enters into the rare medium, it will move away from the normal. As you can see, the third ray, when it strikes the surface, it will move along the surface of the medium. It will bend, it will refract it, and it will make an angle of 90 degree with the normal. So the corresponding angle of incident for such angle of refraction is known as your critical angle. I hope now you will understand what actually is a critical angle. This is a very important short question. Now your next topic is total internal reflection. First of all, we are going to discuss the definition and then I'm going to explain it to you. When the angle of incident becomes larger than the critical angle, no refraction occurs. The entire light is reflected back into the denser medium. This is known as total internal reflection of the light. As you can see in the animation that he give you the 3 processes. One is the refraction, other is the critical angle, and third one is the total internal reflection. As you can see that when your angle of incident is greater than the critical angle, then the light ray will totally reflect back into the same medium. This is the process of total internal reflection. For example, we have the critical angle of water and we have the critical angle of the glass. The critical angle of the water is 48.6. So when your angle is greater than 48.6 degrees, then the light ray will totally internally reflected. It means if your angle is going to be 49 or 50, then the total internal process is going to be happened. But when we are going to talk about glass, then the critical angle for the glass is nearly about 42 degree. As your angle is going to be exceeded from 42 degree, then the light will going to be totally internally reflected, as you can see in the animation. Similarly, the diagram given below, you will see the total internal reflection there, that when the light ray enters from the denser medium, hits the surface, and its angle of incident is greater than the critical angle of the medium, then it will totally internally reflected into the same medium. This is known as total internal reflection. Now we have to make some calculation for total internal reflection, or you may say that we have to find out the refractive index for the critical angle. For this, once again, we are going to use the same theory, that when the light enters in air from water or denser to rare medium, we are going to use the light ray which enters from denser to rare medium. The Snell's law becomes n is equals to sine r by sine I. As your initially we use the Snell's law, which is equals to n is equals to sine I by sine r. As our angle of refraction is formed in the air and our angle of incident in the medium, so our Snell's law becomes for this situation only that n is equals to sine r by sine I. As we know that your angle of refraction in the rare medium is equals to 90 degree, and your angle of incident becomes equal to the critical angle. So I is equals to C and R is equals to 90 degree. Now by substituting these values in the equation, we have n is equals to sine 90 divided by sine C. As we have n is equals to 90, so we know the sine 90 is equals to 1. So n is equals to 1 by sine C. By using this formula, we can calculate the refractive index and we can find out the critical angle for any media by using this simple formula, that is n is equals to 1 by sine C. Now we are going to discuss some simple applications of total internal reflection. Basically, totally internal reflecting prism are used in these applications. Many optical instruments use right-angled prism to reflect a beam of light through 90 or 180 by total internal reflection, such as camera, as you can see in the figure, in which we are going to place a prism, and when the light ray enters inside the prism, it will reflect 2 times. There is a process of total internal reflection 2 times inside the prism, and then the light ray emerges out, strikes the mirror, and you will capture the image. Similarly, if you are going to see the periscope, then you will see the animation that the light ray comes, strike the prism at right angles, and then the reflected ray again strikes the second prism and then enter into the eye and make the image. Similarly, we have binocular, as you can see in the figure, that there are 2 prisms, and we will see that in each prism there are 2 total internal reflection processes, and after going through these processes, you will see the image clearly. You can expand the image, you can contract the distance, Now we are going to discuss the two examples, that is periscope and binocular, in detail. Number one is your periscope. As you can see in the figure, that one of the angle of a right angled prism, as you can see that one angle of your prism is a right angle, that means it is of 90 degree. When a ray of light, as you can see, the object AB is placed and the two light rays are going to be emerged, one from the head of the object and one from the tail of the object. So two light rays are emerged from it and enters inside the prism perpendicularly. As these light rays are going to be entered inside the prism perpendicularly, so these light rays are not going to be refracted. As I have already told you in the process of critical angle, that when a light ray strikes the surface at 90 degree or it is along the normal, then it will not bend, it will move straight away and hit the hypotenuse of the prism. And when it hit the hypotenuse of the prism, it will totally reflect it back, because the critical angle of the glass is 42, and when it will reflect it, it will make an angle of 45 degree with the normal, which is greater than 42 degree. So a total internal reflection process is going to be happened inside the prism, and the light ray is going to be emerge out. And similarly, the light ray which is going to be emerges from the tail of the object, same process is going to be happened there. It will enter inside the prism, moving parallel to the normal, hit the hypotenuse, and then it will reflect back. So again, there is a total internal reflection, and you will find the image as A prime and B prime. On the other hand, when we are going to discuss the binocular, as you can see in the image clearly, the light is totally reflected by the prism by an angle of 180 degree. Two such prisms are used in the binoculars. As I have already told you, that you have the object QP, whose you have the object QP, two light rays are going to be emerged from one from the head and one from the tail. When it strikes the edges of the prism, it will reflect back. Total internal reflection process is there. As you can clearly see, that angle of incident is greater than critical angle of the prism or the glass, which is 45 degree. So it will again moving straight away hit the other surface, and again it will totally reflect back, and it will emerge out from the prism and makes an image P prime and Q prime. You will see an inverted image over there. So in this way, binocular makes the image on the screen with the help of total internal reflection. Now our next topic is optical fiber. What actually is optical fiber? Optical fibers are basically the light pipes. On what principle does it work? It works on the principle of total internal reflection. So total internal reflection is used in fiber optics, which has a number of advantages in telecommunication. Fiber optics consist of hair-sized threads of glass or plastic through which the light can be traveled. As you can see in the picture, the inner part of the fiber optics is called the core, and the outer surface is known as cladding. As you can see in the picture, that core is made from the glass or plastic, which I have already told you, and its refractive index is relatively very high as compared to the cladding one. The cladding is made up again of glass or plastic, but of relatively low refractive index, so that if a weak light ray is entered inside the glass, and it will try to escape out, so strong light rays are going to be totally internally reflected by the core, and if you have a weak light, then it will be totally internally reflecting by the cladding. So in other words, you can say that the all light rays are going to be uh, totally um, totally internally reflective, and we have the 100% signal output on the other side. So there is no losses of the signal. So this is the biggest advantage of using optical fiber nowadays. So that is why your telecommunication and for your internet connection, majority are going to use optical fiber nowadays. Now the next very important thing is your light pipe. What actually is a light pipe? A light pipe is basically the bundle of thousands of optical fibers bounded together. They are used to illuminate the inaccessible places by the doctors or the engineers. For example, if the doctor have to view the internal organ of a body, of a human body, then he can also use the transmit images. He can use the transmit images from one place to another, or he will enter the light pipe inside the patient's body and can view all the internal organs on the monitor, as you can see in the picture. Now next topic is your endoscope. What actually is endoscope? An endoscope is a medical instrument used for exploratory diagnostics and surgical purpose. As you can see in the animation, that you will see one of the endoscope whose one end is connected with the monitor, and the in the other end you will see a camera. So and when you do the endoscopy, it is used to explore the interior organ of the body. Due to its small size, it can be inserted through the mouth and thus illuminates the invasive surgeries. The endoscope used to examine the stomach, bladder, and throat are called gastroscope for the stomach, cystoscope for the bladder, and throat bronchoscope. In this animation, you will see a bronchoscopy in which the doctor inserted an endoscope inside the patient's mouth and see the different ways of the throat, the different openings of the throat, and you will see the side image in which he sees the different position of your endoscopy, that in which part the endoscope is going to be entered and starts to illuminate and give the image on the monitor, and you can see the image on the monitor on the other side of your animation. As I have already told you that endoscopy is used to view the internal organs of the body. So this animation clearly sees the endoscopy of the stomach, which is known as gastroscopy. An endoscope uses two fiber optic tubes through a pipe. A medical procedure using any type of endoscope is called endoscopy. The light shines on the organ of the patient to be examined by entering through one of the fiber tubes of the endoscope. Then light is transmitted back to the physician's viewing lens through the other fiber tube by total internal reflection. Flexible endoscopes have a tiny camera attached to the end, as you can see in the previous one. Doctor can see the view recorded by the camera on a computer screen. So in this way, they will monitor all the internal organs of the human body by using endoscopy. Now today's last lecture is refraction through a prism. Prism is a transparent object, as you can see in the figure, with at least two polished plane faces incline towards each other, from which light is refracted. So in this case, we are particularly discussing a rectangular prism in which the emergent ray is not parallel to the incident ray. As it is clear from the picture, it is deviated by the prism from its original path. As you can see in the figure that incident ray PE makes an angle of incident I at a point E, and when it enters into the prism, it will refract it towards the normal, that is N. As EF, as EF, it is refracted. This is your refracted ray EF. The refracted ray EF makes an angle of refraction which is represented by R in the figure, and it is bended towards the normal. This refracted ray EF is almost parallel to the base of the prism, that is BC, as you can see, and when this refracted ray strikes the other face of the prism, it will emerge out. When it strikes at a point F, it will emerge out from the prism as a ray FS. This is known as your emerging ray, and it is clear that FS is not parallel to the incident ray PE, but it is deviated by an angle D, which is called the angle of deviation. And how do we get the angle of deviation? We will get the angle of deviation when we are going to extend the incident ray in the backward direction in the dotted line, and your emergent ray in the dotted line. When these two backward extended rays are going to be intersect each other, as you can see in the figure that both the rays are going to be intersect each other at point G. So at this point, those incident rays makes an angle, and this angle is known as your angle of deviation. Now, for your practice, I am going to give you few questions by the end of my each lecture. What is meant by the term total internal reflection? State the conditions for total internal reflection. What is critical angle? Derive a relation between the critical angle and the refractive index of a substance. What are optical fibers? Describe how total internal reflection is used in light propagating through optical fiber. All these questions and their answers are discussed already in this lecture. I hope you will understand and enjoy this lecture thoroughly. Inshallah, we will meet in the next lecture. Until then, Allah Hafiz.